Okay, let's go ahead and get started. Okay, so we left off with Chris talking about some various tools for manipulating and stratifying and subsetting and analyzing subsets of data. And then he talked about fitting some of the basic kinds of regression models, including a logistic regression with the GLM function. So hopefully most of you at least are familiar enough with what logistic regression is that even though we didn't talk to you about what the statistical model was, that made some sense to you. So the breakout problem was to think about actually trying to fit some of those kinds of models to the voting preference data. And I said in the email that hopefully you got last night that there is a new version of the voting data set that we put in the zip file and up on Git, and that's a CSV file, and it actually has Bush, Kerry data, et cetera, instead of the 1, 2, 3, 4 business. So it's a little bit more user-friendly and doesn't require you to know what the coding is and have the metadata separately. Okay, so I'm just going to, however, go ahead with the original Stata data file because that's the one that we were working with yesterday. So the first question was just to think about fitting a model to the data just for California. So that would involve doing some subsetting and then adding in some various terms into the model to do the logistic regression. Actually, let me before I say that, let me ask: were there any questions about sort of the context of the breakout problems, or were there any lingering questions from yesterday in terms of topics or difficulties that anybody had with anything either yesterday or as they were potentially working on anything last night? Okay. So obviously this breakout problem could be a whole journal article, and in fact actually could be a whole book. That's basically what this Red State, Blue State book by Andrew Gelman, who's a statistician at Berkeley. He was at Berkeley at Columbia, was about. And so we're just going to scratch the surface here, but at least see the sorts of analyses that you might do and some of the things that you might start to put together to be able to do a complete analysis. Okay, so here I'm just subsetting just to the California data. So I'm just doing the sort of subsetting by rows. The vote state equals 5 is going to create a vector of trues and falses, as we saw a couple times yesterday. That's then going to pull out the rows of the data set that correspond to the California data. And now I'm going to do another subset that's just going to pull out the Bush voters, which were 2s, and the Kerry voters, who were 1s. So I'm just subsetting it down so we can do a logistic regression with 2 classes instead of having to worry about having multiple classes in a multinomial kind of situation. Okay, and then in order to fit the logistic regression, I'm not sure what would happen if we tried to fit the logistic regression with 1s and 2s as the values of the outcome. Did anybody try that and see if GLM doesn't work? Okay. So I was guessing it might not work, and so as my first step here, I didn't try it. My first step here was to recode the Bush equals 2 voters to be Bush equals 0. Now I've got 0s and 1s. Okay, so any questions about that setup or what I needed to go through there? Well, that's interesting. I would have thought I should be putting in family equals binomial here, but for some reason I didn't, and yet I thought it still worked. Well, let's see what happens here. Okay, so let's actually do summary. So I'm just going to fit a minimal model here, which is just doing a logistic regression of the preference of voting 0, 1 for Bush and Kerry on income. Okay, and if we recall, most of the variables in this data set were not continuous, but they were categorical variables. So if we did table of CA income, we'll see it's got a bunch of these different classes, or a bunch of these different categories that we can tabulate into. And we can look and see, is this thing a factor, or is this thing not a factor? Okay, so it is a factor, so that's good. As we've seen and as was discussed yesterday, one of the great things about factors, even though I kind of bashed them earlier in the day, is that they allow you to do this sort of modeling really easily, and it deals with all the dummy variables and all that sort of stuff. Okay, so let's see what we get if we just summarize that basic model. So it does. Oh, okay. Yeah, so it looks like I made an error in the solutions here, and I forgot to tell it to do a logistic regression. So it's not actually doing logistic regression, it's doing a regular linear regression on zeros and ones as the outcomes. So we need to fix that. So if I go, and let's get the help on GLM to see the syntax for the family to be able to specify logistic regression. Okay, so here if I go down here to the family argument in GLM, it says look here in family for information. Okay, so if we do binomial link equals logit, that's what Chris told us yesterday was what would fit a logistic regression. So let me insert that fix into my code here, and now let's run that again. Okay, so actually this is sort of a good experience just to see the sorts of things that will happen as you do things on the fly. So let's look at what the class is of the CA Pres 04. So it's numeric. Okay, so that's good so far. Ah, there are some 9s. Okay. So that's weird. Does anybody, I'm actually a little stumped for the moment here because I ran this line of code and it should have just pulled out the data that were 1s and 0s. Is anybody seeing where my mistake is and why there are 9s in this variable? No? Did I run that line of code? So let's try this again and do it from scratch. Now let's do table of CA Pres 04. Okay, maybe I didn't run that line of code. I'm not sure what happened there. But now let's see if this works. Okay, so now we're going to recode the Bush voters to be zeros, and we're going to fit our model. Okay, now it actually ran. And I could do summary of mod 0, and shows me. It shows. So now this indicates that it does seem to be fitting a logistic regression because it says it's using the binomial family here. And it gives us a bunch of coefficients for the different levels of my categorical variable. So you can think of this as the intercept is for whatever the baseline category is. This is the usual sort of dummy variable coding in these sorts of models. And then the coefficients for the other variables are the incremental effect of being in the other given category. So any questions about the model I'm fitting or what I've gone through here in terms of that basic model? Okay, so obviously if we're fitting a regression model, we're often going to want to include multiple regressors. We want to think about trying at the best we can to control for confounders or to account for multiple variables in the modeling. So let's go ahead and fit a more complicated model than just the regression on income, and I'm going to have to add in each of these. I'm going to have to correct my error in not fitting a logistic regression in each of these models here. So here my thought is, okay, I'm going to fit, now let's sort of think about, well, we know that voting preferences vary by male-female. We know they vary by race as well as potentially by income, that if income is the key thing we're interested in understanding here. So let's include race and sex as variables in the model here and go ahead and look at that. Okay, so this is also another good example of trying to detect an error and seeing what happens as I just go about doing my business in R. Can anybody see what happened and why it's saying invalid type for variable weights here? There's a syntax error. Okay, so people are saying that it looks like there's an extra comma in here. So if this is the line of code I ran, it looked like when I added in the binomial link equals logit, I made a mistake and I added in an extra comma. Okay, so that's one thing to notice. Anybody have an idea of why it's talking about weights when I made that error with a comma? Okay, so it's trying to match by position. That's what Jacob was talking about yesterday. And presumably the next position after data, here's the data argument. Presumably the next position after that is weights. It sees something, it sees a comma, it doesn't see a name for an input argument. It says, oh, that must be weights. Then it sees that there's nothing there, and then there's something about it trying to interpret something as a list. So if we actually did help on, actually we can just use this function args, which you haven't seen before. Oh, it looks like there's a bunch of ... So the ... as we've seen, are going to get passed along to another function. And so somewhere in the guts of GLM, the ... is being passed along, and it's then seeing the space for the argument after that comma, and presumably somewhere in there, it's thinking that should be the weights argument.
You can see it on the first line after data is weights.
Oh yeah, oh right. Okay, great. Sorry, I was looking down here. I misinterpreted the indentation here. I thought this was the beginning of the argument. So okay, so formula, family, data, weights. Indeed, that's the one after data, and that's where it's thinking that it's trying to find this missing argument. Okay, so a little bit of sleuthing often allows you to sort of understand where these error messages are coming from and sort of detect what's going on. Okay, so that fit. That's good. And I could do a summary on that model, and we can see what's happening. Let me give myself a little more space here. So the 1 is Kerry and the 0 is Bush. So positives is a greater propensity to vote for Kerry than to vote for Bush. So we can see here that some of these things make quite a bit of sense. There's a pretty large coefficient for black, which we know, if we know anything about American politics, that most African Americans vote Democratic. There's a pretty reasonably large coefficient for Latinos. Same for Asians as well in this. And there's also at least a moderately large coefficient for female. So all of these reflecting the preferences of voters and groups that tend to vote more Democratic. And then relative to the baseline category, which I guess we have to sort of ferret out what the baseline category is, presumably the baseline category, and we could go back and look at the levels of the factor variable and figure out what the first one was, and that's presumably going to be the baseline category in my model. But presumably what that is under $15,000 in income. So all of these are negative, suggesting that voters are less likely to vote for Kerry, more likely to vote for Bush, relative to this baseline category, which might presumably be, sort of is, we can see from the estimates, is rather more Democratic leaning than these higher income groups. So obviously there's a lot more you could do here. You could do sorts of model comparisons where you compare a larger model with a smaller model and try and do F-tests, and although I guess in this case it would be a likelihood ratio test to compare models and do those sorts of things. So any questions about what I've done here? Okay, the other thing I did was I fit a couple stratified models. I fit a model just for whites, and I fit a model just for blacks. I'm not sure that I'm going to bother to go over the results of those here. So let's just go on to the prediction phase. So obviously it's a little hard to interpret the coefficients of a logistic regression model because they're on the scale on the logit scale. So we have to do back transformation to do inverse logit kind of stuff to get out the estimates of the probabilities of voting for Kerry and Bush. And as you might expect, there are helper functions, auxiliary functions in R for doing those sorts of calculations. So I suggested that you go and look at the predict.glm function and see what it does and what its arguments are. And this is another one of those functions. We saw the function summary, and we saw that if you apply summary to a vector or if you apply summary to a model object output, it does different things because there's this generic function summary that looks at the kind of object that you're passing into it, and then it's going to dispatch the correct type of specific summary function relevant for the particular object that you're using the summary function on. predict is another one of these kinds of generic functions where there are specific ones for different kinds of objects. And this is one where you might expect, there are lots of different kinds of statistical models, machine learning kinds of models, where it's a model that you fit to data and then you might make predictions with it. So you might expect there might be many, many different kinds of predict functions. Maybe there's one for a neural network, and there's one for a GLM, and there's one for random forest, and whatever your favorite statistical model or prediction method is, you could presumably write a predict method that would apply for that one. So predict.glm does that for our case here. If we did help on predict.glm, one of the things it'll tell us is there's a new data argument, and if you delve into what that says, it says optionally a data frame in which to look for variables with which to predict. And if omitted, it's just going to tell you predictions for the actual data values that you pass in. So did anybody, when people were looking at this help information, did that confuse people, or were people able to sort of figure out what was going on with that, or any observations about that? Okay, so what I did here was I said, okay, I'm going to use the predict function, and I want to predict. I'm just going to predict for one particular kind of person. I could have given a data frame with many, many rows and made predictions for all of those different levels of the different regressors. But here I'm just going to make it simple and just do a single call for each type of person. So I'm going to say, okay, let's make a data frame where I say the person makes 75,000 to 99,000, they're female, and they're white. And that's my data frame. These names of the variables have to correspond exactly to the names of the variables that were used in fitting the model, because R is going to need to be matching up the fitting of the model that got estimated with now running new regressor values through that model to make the predictions. So that has to line up exactly. But we can do that, and it's just, that didn't work, did it? So it gave me, okay, I said immediately that didn't work. Why did I know that didn't work? In some sense, because I got a negative value, and I was thinking I wanted to get probabilities out. So any thoughts on what's happening here? What other kinds of predictions could I get from a GLM? So I could predict on the scale of the link function. I mean, I could just be predicting on the scale of the linear predictor, which is presumably what's happening here. So that would then lead me to say, well, is there some way to tell the predict function that I wanted to predict on the scale of probabilities instead of on the scales of the x beta of the linear predictor? And indeed, if I look in the help, it says there's a type argument and the type of prediction, and it says the default is the scale of the linear predictor. So as I just suggested a second ago. And then the alternative response is on the scale of the response variable, which in this case is the 0, 1 variable. So it says for the binomial model, the default predictions are of the log odds, the probabilities on the logit scale, and type equals response gives the predicted probabilities. So I need to go back and make that change here. You'll notice I'm using quotes, either single quotes or double quotes, sort of willy-nilly here, and in most cases it doesn't really matter whether you use single or double quotes. The other thing you might notice, just as sort of a minor side note, is I often put a lot of spaces in here, and the reason is just to sort of space stuff out and make it easier to read. Yeah, there's a question back there for me or for? Okay. Okay, so let's see if that works. Okay, so now we've got an estimate of 38.5% probability of voting for Kerry for a voter who is female, relatively well off, and white. And if I change that to a female who is less well off, we see the predicted probability goes up to about 55%. It's actually lower than I might have expected. But and then if we change it to be a black woman who is relatively well off, we see the probability goes up quite a bit, up to 75%. So you can sort of query the model and get some sense of what the model is doing. Questions or comments about that? Okay, and then I sort of gave sort of an ambitious problem of doing a bunch of stratified analyses. I think I'm not going to bother to go over that, but if you're interested in that, you can see that I used a split and then an s-apply to do some stratified analyses by state. So we've seen some of this You could also use the sorts of tools that, I think you could use the sorts of tools that Chris talked about yesterday to do this sort of stratified analysis. And I also put in the zip file some data on more recent average state income. And so if you could look and see if the effects of being female, for example, the effects of income at the state level from running the individual regression on the individual people, you could see if those effects vary by the aggregate state level income or other aggregate state level information to try and get some sense of how do things vary by state and can we relate that to other sort of demographic characteristics of the state. So that's all in the solutions. Obviously these solutions have a few errors in them that we've discovered as we went through them, so be aware of that, and I'll try and remember to correct that and post new corrected versions of these. Okay, questions or comments before I move on to the next module? Okay, so let's look at Module 7. This is sort of a grab bag of a few different things, but all very useful things. So let me just again load in this sort of preparatory stuff, although I think that was all essentially already loaded in. So one of the things that R allows you to do is basically optimize any arbitrary function. So find a minimum or a maximum of a function. So if one were fitting a model, for example, with maximum likelihood, and you didn't have a closed form solution, you might be taking the log likelihood and maximizing the log likelihood. Or if you have like a lasso model, you might be optimizing some penalized log likelihood or penalized objective function. So just as an example of the sorts of optimizations you can do, I'm going to show you a sort of funny looking function, and we're going to see R do the optimization over that. So this is something called the Rosenbrock banana function, which kind of looks kind of cool when you see it, and you'll understand why it's called the banana function. But what I'm going to do here is, for plotting purposes, we haven't really talked much about plotting, but you'll sort of see a bit of it here, and then Chris is going to show you some stuff. I'm going to create a grid of values on what I'm going to call the x1 axis and a grid of values on the x2 axis. And then I'm going to evaluate my function at all pairs of points along those two axes so that I can get essentially a gridded representation of what this function looks like. And then I'm going to plot that. So I use this function called expand.grid that figures out all pairs of points of my x1 and x2 values. So I'm taking x1 and x2 to be a sequence from -5 to 5 of length 100. So that's my grid in both of the dimensions. And then this expand.grid, we can see what it does. Let's actually look at X. Oops. So it looks like X made sort of strung out everything for all possible pairs of X1 and X2. And in fact, if I could, let me do the head of X. So it's done. So it's holding the second one constant at -5 and looking at all of the values of the first one, and then it's going to cycle through all possible pairs of X1 and X2. And now I can use my function apply that we saw yesterday to evaluate the function, the banana function, at each of these x1, x2 coordinate values. So you can see this is something that you might, if you came in to this not having seen stuff yesterday, you might think, oh, I'll write a for loop to run this function on each of the coordinates. But there's this functionality that I can, with apply and with doing this expand.grid, where I can do it all quite nicely and quickly. And not without writing a lot of code. Okay, so now I'm going to plot the function, and part of the reason I went through all those machinations of setting it up exactly that way is in order to use this image function that's going to show me a color scale map of the function, I need to have the grid of values on the x1 axis, the grid of values on the x2 axis, and then I need to make a matrix of values representing the function evaluated on my two-dimensional grid. So if I then do that, and there's some additional stuff about graphics here. What am I doing here? Well, MF row is the way I make a layout of multiple plots in a given window. So this is going to make a matrix of plots with one row and two columns. That's what the C of 1, 2 stands for. And the MAI is just sort of manipulating some of the margins of the plots. You don't need to worry too much about that. But I was trying to manipulate the white space around each of the plots. And then since I've said I'm going to make a 1 by 2 layout of plots, I'm now going to call do two separate plotting calls to fill in those two plots. And I'm going to use this image.plot function that comes from the fields package. So if people are following along, you'll need the fields package both installed and loaded into R to be able to do this. Okay, so that's what gets created when I do this. Let's give ourselves a little bit more room. Hopefully that will adjust on the fly. So on the left side, I just did image.plot directly on the banana function. And you can see that it doesn't really give us a very good sense of where the maxima or minima are of this function because the scaling is so wide. And the range of values of the function, at least over this domain, are fairly large. So it's a little hard to tell where the minimum is. So what I did, and this is sort of a common thing that you might do in these contexts, is I took the log of the banana function, because the minimum of the function is going to be at the same place as the minimum of the log of the function. And that indeed reveals the fact that it does look sort of like a banana. I'll see if I have any luck with my pointer for a little while at least. So we can see that it's this function that takes this shape that would be sort of a little bit complicated to optimize because it's not a simple linear function or anything like that. So that's the thing we want to optimize over. And in this case, we're going to try and find the minimum of this function. And if we look at this, we can see, well, the minimum probably occurs somewhere down here. So the task for our optimizing routine is going to be to find that place. Okay, any questions about what we're trying to do here or the setup of the problem? So most optimization problems are going to be a lot harder than this because we wouldn't be able to just graph them and see more or less what things look like and more or less where the minimum is. And usually when we're doing optimization in higher dimensional spaces, we're basically sort of operating blind. We can sort of take slices of two-dimensional slices of a function, but we can't actually see the whole picture because we just don't work very well in higher dimensions. Okay, so what do I do to optimize? Well, there's a function called optim that takes a starting value and then takes a function and then does the optimization. And I guess I have to hope that by default it is going to do minimization because otherwise I'm not going to be able to get a reasonable answer out of this. So let's look at help on this. So it says general purpose optimization. It talks a little bit about different kinds of options it has. Is anybody seeing here anything about minimum or maximum? Okay, minimized or maximized. Looks like the default is going to be minimized because it says that first. So that's presumably why in my demo here I didn't actually say do anything explicitly to tell it to do minimization. Okay, so it does the minimization and it gives me back, as you might expect, what does it give me back? It gives me back a list because it wants to give me back a whole bunch of sort of heterogeneous information about the results of doing the optimization. So the first thing it gives back is the value of the x1 and x2 values where the minimum was found, right around 1 and 1. And the value is the value of the function evaluated at that minimum or hopefully minimum that was found. And then it tells us something about how many times was the function evaluated. If we had given it gradient information, it would be evaluating the gradient as well to aid in the optimization, and it would have had something other than NA here. And I believe the convergence of being 0 means that it did actually converge, which is a little bit funny because usually we're thinking true false as being 1 as being true, but here you would interpret it differently. Okay, so it looks like it probably did a pretty good job. If we go back to our plot, it does indeed look like 1, 1 is right around where the minimum is just by inspection. And hopefully this will work. I was just going to try and show the progression of points as it did the searching to try and find the minimum. So I just injected into the banana function, I injected a little plotting here. This is not the best, this is not the most sophisticated way to do this. And then I said sleep for a little bit, just pause the execution for a little bit, because otherwise it would do it so fast that you wouldn't be able to see it as it moved around. So that was why I have this little pause in here. So let's see if we can get that to work. So now I'm just going to make one image of the function, and I'm going to plot the function originally, and now as I run the optimization is sequentially going in and using the banana function. So it should be sequentially going in and drawing a point on the graph every time it evaluates the function. And it takes a vector as an input, that's this x, and so I'm telling it to do points, which says to plot a point at the combination of x1 and x2. Okay, so now let's rerun our optimization with our modified banana function. That's not working very well. So some of these things seem not to work great in RStudio. Oh, there we go. Okay, well, it sort of did it all at once. That's a little bit unfortunate. So it doesn't seem to be doing the interaction with the operating system and the sleeping in quite the way that I was hoping. But I guess I'll just tell you sort of what happened when I ran it on my own machine, which is it started out over here, sort of bounced around for a little bit, eventually made its way over here. It sort of overshot in the sense that it sort of went over the valley, and then I think it came back. Or maybe it came down here and then it was at some point at which it did that evaluation up there. And then eventually it got to here, and then it was sort of a straight shot to basically just follow the gradient directly down the valley. And so then it sort of went meandered down, eventually meandered down there and got to the minimum. Okay, any questions about that? So that's useful for general optimization. I just wanted to mention a little bit about doing sort of smoothing and non-parametric modeling. So we've talked about linear regression. We've talked about generalized linear models. All of these are linear in the parameters, linear in the regressors, at least on some transformed scale. So another thing that's pretty common and helpful to do is to be able to fit basically a smooth relationship between some x variable and some y variable. And so a common way to do this is to use something called an additive model or a generalized additive model. And that's basically additive model and linear model and generalized additive model and generalized linear model are sort of the pairings that you can think of. And so what you can think of is, okay, we have, let's just think of linear regression. If the data are not, sorry, you're probably not going to be able to see these very well in the back. If the data don't have a linear regression between whatever x and whatever y is, we're obviously not going to be able to fit a very good linear model. But if we had some way to sort of fit a flexible model, we might be able to fit a flexible relationship between x and y. So that's the basic goal here. And as a matter of, we can obviously think if we have multiple regressors, we could fit some very general flexible surface in a very high dimensions that could have all sorts of crazy bumps and wiggles. And that's going to be pretty hard to fit because there are just a lot of terms in the model, and we're likely to end up overfitting. So the idea of an additive model is that we're just going to have, we can have these smooth functions of x, but if we start having multiple x's, we're basically going to have a model that's a smooth function of x1 plus a smooth function of x2 plus a smooth function of x3, and so on and so forth. And that's where the additive comes from in this terminology. So if we can look at this using this data set with the earnings and height that we've been seeing a bunch. So this package called MGCV fits these generalized additive models. There was something weird going on with the random number generation that made me need to call to just do a sort of throwaway call to a random uniform at some point. But here's the basic syntax. I'm going to fit one of these generalized additive models where I regress earnings on height and earnings on education. And I'm going to do it just for males because there might be different things going on for men and for women in terms of the relationship. And what I'm doing here is I'm saying fit a smooth relationship between height and earnings and add to that a smooth relationship between education and earnings. And the k equals 10 is basically an upper bound on sort of the degrees of freedom that are allotted to the smooth. So the basic idea is if you think of a linear regression as having 1 degree of freedom for the slope, and if you have a quadratic regression, you have 2 degrees of freedom to parameterize a quadratic curve, and a cubic relationship, you have 3 degrees of freedom. This k equals 10 says at most I could have 10 degrees of freedom or sort of up and down a number of different times in the relationship. But actually what this does, there's some nice statistical methodology work behind this. It actually uses the data to choose what degree of smoothing and how many effective degrees of freedom to allot to fitting this relationship. So there's some statistical magic going on behind the scenes here. So that's the model we're going to fit. I'll do it also for women. And now if I do summary of my model for men, what you see is it shows that it's estimated some smooth relationship of height, and from the data it's estimated an effective degrees of freedom of 1, which basically just means it's estimating there is a linear relationship even though we allow it to estimate a more complicated nonlinear relationship. But for education, it's estimated that there's a nonlinear relationship and it's allotted 5 degrees of freedom to that for that part of the model. So it seems to think there's some nonlinearity in the relationship between education and earnings. So that's useful and helpful as far as it goes, but it doesn't give us a very good sense of sort of what's going on in the fitting. So let's actually we can look at the female model as well. So that's interesting. It looks like there's less nonlinearity in the female model than there is in the male model. We could think about whether that makes sense or not from a substantive viewpoint. And let's do some plotting. Again, this plot function is just like the summary function. It's just like the predict function. There are these S3 methods where there's a particular specific plotting function that's been written for these generalized additive model objects. So it's going to do a particular kind of plotting specific to the kind of model that we fit. So here is what we get. Actually, let me go back and just plot the male model. All right. I'm not sure what it's doing here with not letting me up arrow very well. So this is what we get as our plot of the estimated effects of height and education on earnings for men. So here's height in inches. So here's roughly 6 feet here. Here's 5 feet here, and we can see it does indeed seem to have estimated a linear relationship between height and earnings. And we could monkey with the plots to see what the values on the y-axis are. They might be a little bit difficult to interpret. They're all relative there because they're relative to an intercept and that sort of thing. But we can then also look at the education relationship, and it looks like, and these are error bars on here, it looks like there's sort of a roughly linear relationship between years of education and income until we get to about 14 or so years of education, and then it looks like there's some nonlinearity in the relationship. So obviously, if I were a labor economist, I'd be doing a lot more. I'd be thinking about this a lot more carefully and trying to make sure this makes substantive sense. That maybe there are sort of greater returns to scale, greater returns to education as you get more educated in terms of income. Obviously, I'm just spinning a story here without knowing too much about the context. So any questions about what I've done here? You stretch a question for someone else. Okay. Okay, so I just sort of wanted to give you a feel for some of the sorts of things that you could do with model building in R. I think I do a little bit more here where I add in race, and there's actually an error in this code, a statistical error in fitting this model here where I added race in. So if you're interested in playing around with that, you could see if you can figure out what the error was that I introduced here and what it was that went wrong, where it was that I went wrong. But let's move on to talking about how R handles distributions. So sort of like I said about losing my train of thought. Sort of like I said about missing values, there are some of the things that R does really well is because it was developed by statisticians and we have a particular viewpoint on the world of what things we need to deal with. So distributions are one of those things. Obviously, distributions are sort of our bread and butter, and so R, from the ground up, is built to deal with distributions as sort of a fundamental piece of what we do. So there's a whole. Let me introduce sort of the nomenclature for this, and this is sort of like the ddply that Chris introduced yesterday. That there's sort of a naming convention here, which is that if I want to do things with a normal distribution, there are 4 different functions that do sort of fundamental things with a normal distribution, and they're named dnorm, rnorm, pnorm, and qnorm. Norm for normal, and the d, p, q, and r for different things I could do with the distribution. And for another distribution, like say the uniform distribution, there's a d-unif, r-unif, q-unif, and p-unif. So there's always a d, a p, a q, and an r function for every distribution, and you just need to match up what you want to do with what distribution you want to do it with. So when I do dnorm, that's calculating the density of the distribution. So if I draw out the PDF of a normal distribution, that's going to calculate, for any x value, it's going to calculate the height on the curve. rnorm will generate a value from the normal distribution. We've actually already seen that. That's pretty straightforward. Pnorm is the cumulative distribution function. So pnorm is going to calculate for some other variable. Let's just stick with this x. Pnorm is going to calculate the probability of being less than x, so the area to the left of the curve. And Q norm is the inverse CDF, so if you give Q norm a value between 0 and 1, say 0.25, Q norm will tell me the value along the x-axis where I have to go, such that 25% of the probability mass is to the left of that value. Okay, so those are sort of fundamental building blocks if you took an intro probability class or an intro stat class that you would have seen. And we can do, R basically has essentially any distribution that you can think of built in, so you don't have to worry about manually dealing with distributions, because either it's built into R or somebody's written a package that adds on the functionality for the particular distribution they were interested in. So I can do things like, what's P norm of 1.96? So we know that's the upper 2.5% cutoff of a normal distribution. So not surprisingly, it says there's 97.5% of the mass to the left of 1.96 in a normal distribution. If I do Q norm, right, that's the one that goes backwards. If I do Q norm, I want to know what's the upper 2.5 percentile of a normal distribution. So I do Q norm of 0.975, 1 minus 0.025. That's going to tell me that indeed that's right around 1.96, the usual kinds of cutoffs of a normal distribution. If I want to find the density, or in this case the probability mass function for a binomial distribution, for a discrete distribution, it's the same sort of nomenclature. I do D and then I use the distribution that I'm interested in. So D norm, and you shouldn't be surprised by now to see that I'm giving it a vector of values, and it's going to be able to handle this sort of stuff in a vectorized fashion as well. So if I do D binom of 0 through 10, where the number of samples is 10 and the probability of success is 0.3, it's going to say, okay, the probability of getting a 0 is 2.8%, the probability of getting a 1 is 12%, the probability of getting a 2 is 23%, the probability of getting a 3 is 27%, et cetera, et cetera. I can do D norm of 5. That tells me that if I go out to 5 on a normal distribution, I guess this should be centered at 0, which it doesn't really look like it is, depending on how I've drawn the lines here. But if I go out to 5, that's pretty far out in the tail of a normal distribution, so it says the density out there is 1 times 10 to the minus 6. But most of you have seen a t-distribution relative to a normal distribution. We know that a t-distribution has fatter tails than a normal distribution. So what if we took a t-distribution with 1 degree of freedom? That's a Cauchy distribution. It has very fat tails. It has a normal density, it has a density out there of 0.012, which is order of magnitude. It's not particularly large, but it's still orders of magnitude larger than the tail of the normal distribution that far out in the distribution. And we can very quickly do sort of illustrations with this. I'm going to create a grid of x values from -5 to 5, 100 of those values, and then I'm going to evaluate the normal density on that grid of values, and then I'm going to evaluate the t-density on that grid of values, and I'm going to plot them, and then we can see what it looks like in terms of the tails and the center of the distribution. So it's really easy to play around with distributions and get a sense for these things in R. So here's the normal distribution in black, and I told it to plot the t-distribution in red. So this is really just a collection of points along each of these two curves, because obviously with a computer we can't do anything really continuously. But because I gave it enough points, R is just basically connecting the points, and it looks smooth because there are a sufficient number of points. And so we can see what we'd expect, that the t-distribution is lower at the center and is higher out in the tails. I can also do things like sampling from a multinomial distribution where I have 100 trials and I have a vector of probabilities of the different categories. And I'll get something like, oh, okay, 8 of them fell into category 1, 10 fell into category 2, et cetera, et cetera. And this is an example I think I won't bother with, but this was an example. If you wanted to know what a chi-square distribution looked like, which is used for things like a likelihood ratio test, you could actually plot the chi-square density and see what it looks like. Okay, so questions or comments about this distributional stuff?
Is there like a list somewhere
of all the distributions? Yeah, that would be handy now that you mention it. Well, let me do a try and see if this does anything for me. Hey, I literally didn't know that I could do that. So I in some sense got lucky, but R is often good in that way. Yeah, so it looks like there's a nice list here of the various distributions that are built into the stats package in R. So let me say a little bit about packages. R has a few sort of core packages that come with R by default. One of them is the stats package that has all of sort of the basic statistical functionality, I think including the LM function and probably GLM as well. But it looks like the distributions that come in the stats package are these that are listed here. But there are lots of other packages that people have written code for other distributions as well. And I'll talk a little bit about getting help with R online in session 4, which is not been covered yet because I skipped over it. Other questions? Actually, that was a good question, so I should go back to my rewarding for good questions. Oh, sorry. Okay, just a couple more things in here. We've actually seen this already, so I guess I can sort of skip over this. We've already seen that we can take a random sample from a set of values. So we've already seen the sample function, and you've actually already used that, so I don't really need to say too much about that. One thing that I will introduce here is if you want to sample from, say, 1 up through 100, one way to do that instead of creating a vector 1 through 100 is to say, use this function called seq length. And so if I do seq length of 100, it'll give me back 100 values. If I say seq length of 0, it'll give me back 0. The reason this is useful is sometimes you might put 1 up through n, 1 colon n in, say, a for loop or if you're doing sampling. And maybe the n is not what you expected it to be, and maybe n is actually 0 instead of 100, something like that. So if I do 1 colon 0, and if I were to do, what I get is 1 and then 0. So like it sort of goes backwards because it sees the first number is larger. So if I had a for loop and I was expecting I did for I in 1 to n, and suppose n was 0, I was expecting it to go 1, 2, 3, 4, and maybe there's an error in my code, and then it goes 1 down to 0, and that is probably a bug. So this seq length is a good way to sort of not write it explicitly as the colon, but to have it be sort of focused on this context of trying to create a sequence of a certain length. Or there's also the seek along, and what seek along does is if I had a vector 1. Let's just create a vector for the sake of having a vector. Now if I do seek along vec, it'll give me a set of indices that move along that vector. This is sort of a bad example because vec already was 1 to 10. But if vec were random normals 1 to 10, then I can do seek along, and that'll also give me a set of indices that will allow me to march along the vector. Okay, let me say a little bit about random numbers because now that we're talking about doing random sampling and taking draws from distributions. So as some of you may know, when we generate random numbers, they're not truly random. They're generated on a computer, and they're generated by a pseudo-random number generator algorithms. And so basically the standard way you generate random numbers is first you use some sort of algorithm to generate something that behaves almost as if it's a random number, that lies uniformly between 0 and 1. And then you have there are various algorithms that would allow you to transform that to, say, a normal random variable or a Cauchy random variable or these other sorts of, or a vector of correlated random normals. There are a whole bunch of these algorithms. So the key is to be able to generate, since we can start with a random uniform and get to any kind of random number we want, the key is to be able to generate random uniform values between 0 and 1. And what happens when a computer generates those via various algorithms that I guess mostly computer scientists or probabilists or statisticians have developed is it's actually pseudo-random in the sense that it's a deterministic sequence of numbers that behave as if they're random. And eventually, after a very, very, very long time, the sequence is going to repeat and come back around to the beginning. So when you tell R what the seed is, you do set.seed, which I think we've seen sort of in passing before. You're basically telling it where along the sequence to start taking the pseudo-random numbers from. And then R, as it needs new random numbers, it's going to then pick them from that sequence moving along. So the danger is that, well, there are two things here. One is we might want to be able to replicate what we did. So if I've done something that involves random numbers and I've done an analysis, and then I send the code to my collaborator and they try and rerun the analysis, they're going to get a different answer because of the fact if they don't use exactly the same random numbers that I used. So we want to be able to go back to the place in this sequence exactly where I started my random numbers and have you start your random numbers there so that our answers will agree and that we can repeat the analysis. So that's one use of setting the seed, the starting point in the random number sequence. The other is that if I were, say, doing generating random numbers, say on two different computers and then combining the results, I want to make sure I'm not just using, and I wanted to have actually random numbers that were not the same, then I would want to not start my seed in the same place on the two different computers. So I'd want to have the seed for the first computer here and the seed for the other computer way down here so that my random number sequences don't overlap. So the seed is useful for that. I'll say a little bit more about that when we talk about parallel processing this afternoon. But if just as a demonstration, if I say then and the seed that you give it is sort of arbitrary. It's just going to by some algorithm, it's just going to choose where in the sequence to start the random number generation. So if I say set.seed of 0 and then generate 10 random normals, there they are. If I generate another 10 random normals, these are going to be different numbers because I haven't reset my seed. And so I've got the first 10 and then the next 10 are generated here. But if I now set my seed back to 0 and generate another 10 random numbers, these should be the same 10 as I generated the first time around. So the one starting with 1.2629 here. So I generated 10, I generated another 10, then I set the seed to go back to here, and then I generated the first 10 again. So that allows me to replicate what I've done. And it's good practice. What happens a lot in my work with grad students in statistics and helping them with their code is that they'll run their code, and for some reason their code will fail at some point. And they'll come to me and say, why isn't my code working? What happened? What went wrong? And I'll look at it and I'll try and rerun what they ran, and I won't be able to regenerate their error because of the fact that they didn't set the seed to start with. So I can't replicate exactly what they did. So that's another case. Finding bugs is another case where it's useful to set the seed in advance so that you can really rerun stuff from the beginning. Okay, and then I have some stuff here on dates and setting dates and times. Maybe I'll say something briefly about that, and then we'll do the breakout. So there are various add-on packages for doing dates and times. I forget if this is part of an add-on package or not. But I can enter my dates in different formats. So here I'm entering a few different dates using this as.date function, and I tell it the format is months separated from days by dashes or separated by slashes or that sort of thing. And this again uses this idea of having objects in R that have a class like we saw for LM and GLM. And I can concatenate dates. I can ask what are the weekdays of these particular dates. So there's a lot of date and time functionality built in that if you find yourself writing a function that does anything with dates and times, step back a second and say, somebody probably already dealt with this already. I probably don't need to write this function again. I can add 30 to a day, and it's going to give to this vector of dates, it's going to give me a reasonable set of the dates 30 days later. I can subtract dates and see what the difference is in terms of time. And underlying it, it's just storing these dates as numeric values relative to some origin time, which I think is January 1st, 1970. Yeah, right. I'm not sure who chose that, although I like it because it's kind of near my birthday. So, and you can also have times as well built in. And there's some help information on working with that. So let's do the breakout here. So this asks you to do some random sampling if you wanted to set up some cross-validation to break out a set of observations in a data set and assign it to 10 different groups to do 10-fold cross-validation. So go ahead and try your hand at that. I gave you a few hints here. And the second one, if you have time, is to demonstrate the central limit theorem. So the idea is if suppose I represent a whole bunch of random numbers as a matrix. So suppose I have n values, and then I repeat my generation of 10 random numbers many, many times, m different times. If I take the mean of this row, if I do that a lot of times, if n is small, the distribution of these means is not necessarily going to look normal. But the central limit theorem says, regardless of how I generated the numbers in here, essentially, if n is large, then when I collect all the means of the rows, that's going to look like that's going to look normally distributed, because the mean is under the central limit theorem is normally distributed. So the idea is to write some code to actually demonstrate that and to avoid doing any looping. So there's the breakout. Take maybe 10 or 15 minutes and work through that, and we'll be around for questions. Okay, let's go ahead and reconvene. So I just put the Module 7 solutions up on GitHub if you do want to download those and see those. In talking to one of you, you had I think a better solution to this than I did, although I'm probably not going to be able to replicate that on the fly. But that also illustrates there are usually about 10 different ways to do things. So I'm just trying to do the setup I would need to do cross-validation. So I want to take a data set and assign a number from 1 to 10 to each of the observations in my data set so that I split up the data set equally into the 10 folds, or as equally as possible. So I'm saying, so this is another illustration of I'm trying to name everything here so that I'm not using sort of magic numbers floating around and everything has a meaningful name. So I say, okay, what if I want 10 folds? And I'm trying to do this generically so it would work if somebody told me, oh, you know what, actually I want to do 6-fold cross-validation instead of 10-fold cross-validation. So I say, what's n? How many observations are there in my earnings data set? Well, there are 20, 29. That's not going to divide quite equally. So let me create a temporary variable. That's going to be the round of the number of observations divided by the number of folds. So that's going to be 203. So then I say, well, how many observations do I want in each of the 10 folds? So I decided, there are other ways to do this, but I'd divide it this way. I'm going to say, let me make the first 9 of the folds, let me have them have 203 observations. And then the last fold, let me have it however many there are remaining. So that's what I'm doing here. I'm doing rep of temp, which is 203, 9 times, or n folds minus 1. And then I'm doing n minus however many are in the first 9 folds to get the size of the 10th fold. So I create a variable called fold size. And if I look at fold size, just did tab completion there, remember that. We see the last one ended up being 202 rather than 203. So that's a pretty nice split. I'm pretty happy with that. I have a little error message in here. So I could take all this code, for example. It's not in the form of a function right now, but I've started to add in some sort of checking and error warning messages that if I did put it in a function, it would have some error checking built into it. So I say, okay, if the sum of the number of the sizes of the folds is not equal to the number of observations, there's obviously a problem. I won't run that now because I know it's fine. And then I say I just created sort of a holding variable for the fold, the assignment to groupings, which is 1 up through 10, and the number of times I'm going to repeat the values 1 up to 10. Each of them I'm going to repeat whatever the fold size is. So this says 1 up to n folds is just 1 through 10. This says I'm going to repeat the value 1, whatever the first value is in fold size. I'm going to repeat the value 2, which is the second value in this first vector. I'm going to repeat that 203 times as well. I'm going to repeat the third one 203 times all the way up till the 10th, the value 10 I'm going to repeat 202 times. So this just creates a vector of the appropriate numbers of 1s, 2s, 3s, 4s, up through 10s. So actually, remind me of what your solution was to do that?
Yeah, so what I did first was,
Yeah, I know I'm putting you on the spot.
okay, give me 1 second to scroll there. Let's see, I did the rep int for 1 to 10, about as many times as we need, so like 203 times. I guess you could save that into a variable or something.
Okay.
And then what I did was, since you pointed out that I could assume that the data was random, I sampled from that without replacements.
Okay.
To fill that in as the column.
Okay. So you created I created this variable fold eventually after a few lines of code. It looks like you did that a little bit more efficiently than I did by just doing this rep 1 to 10. And if we do table of your solution, we get, okay, so this is one too many observations, right? This is 203 in each of the groups. So if we got rid of one of those, I don't know exactly how you created the variable, but yeah.
I just sampled it 29 times.
Okay, yeah. So if we could then, and then the key is just to sample from that, and both my solution and your solution then say, okay, I need to randomly sample from from the values 1 through 10 in the right way so that I'm sure that that things are randomized, because I don't know the data are going to come in any random ordering, are going to come in a random ordering. So yeah, so I have another check in here. I set my seed, remember replication, replicability. This is particularly important here if you're going to tell somebody the algorithm that you use to decide on your cross-validation procedure. You want to be able to tell them something whereby they could replicate it easily. And obviously you could tell them what the folds are for the observations, but it's nice to be able to just tell them what the code is that would give them the folds. Yeah.
Sorry, why 203?
203 is just because there are 2,029 observations in the data divided by 10. That's roughly 203 per. Yeah. And then I'm just going to sample. Hopefully this is without replacement by default. It's possible there's a bug in here. I'd have to go back and remember what the default is. Then I'm just going to do the random resampling, and I'm going to assign it into the earnings data set, so I have a new column in the data set. So if I did table or head of earnings, I should see that I now have folds or groupings assigned to each of the observations. Questions, comments, complaints? Okay, so the problem was a little probability or statistics problem. So I did this in a way that's somewhat generic and does a little bit of plotting to illustrate the point. You probably proceeded in a somewhat different way. But I did this so that I said, okay, I was saying here that the extent to which the central limit theorem applies is basically the number of observations that go into the vector from which I calculate the mean. So I'm going to write my code such that I can do this for any length of row here. So here I'm going to have my sample sizes be either 10, 50, or 300. I'm going to create a function that will operate on that, on whichever of those I choose. So I'm going to create my little plot fun, which takes n, which is the number of observations going into the mean, num reps, which is the number of times that I'm going to replicate this procedure to then be able to create a histogram and see if it looks like the mean is indeed normally distributed. And what do I do here? Well, instead of doing any sort of looping to create all these random numbers, these are all just independent of each other. Right? So I can just create a vector of n times n reps, num reps or m, random variables, and then just put them into a matrix in the right dimension. So here I'm going to choose to say, well, let me test and see whether a chi-square random variable, if I take the mean of enough chi-square random variables, is that going to look like it's normally distributed? So I chose a chi-square because with a small number of degrees of freedom, it's going to be a skewed distribution that butts up against 0. So I'm generating n times num reps random chi-square random variables, where n reps by default, oh, there's a bug in my code. It will work in this case, but this, you notice I have n row here as 10,000 instead of n row is num reps, which is what it should be to be fully generic. So I'm going to create this matrix n by num reps. I'm going to use my row means to find the mean of each row, and then I'm going to just do a histogram right away on that. All right, so this is just a few lines of code to be able to illustrate this point. So there's my function. I forget if I ran that line of code. And we're going to, whoa, that's not what I want to do. Okay. So we've sort of seen this a bit helter-skelter in terms of what this par command does to set graphics plotting options. But here I'm going to create, remember we saw that I could create a 1x2 matrix of plots before? Here I'm going to create a 1 by however long the sample sizes is matrix of plots. In this case, it's going to be a 1x3 matrix of plots. Again, there's a little bit with monkeying with the margin sizes here. And then I'm just going to s-apply my plot fun to the different sample sizes. So again, you can sort of see the power of what you can do in R with pretty few lines of code, and hopefully, particularly as you get used to it, fairly clear lines of code of what it's doing. So hopefully this illustrates the point. If we have an n of 10, I should have actually plotted what it looks like, just a chi-square with one random variable just to hit home that it is a skewed distribution. But we can see when we have 10 that it's still somewhat skewed. It looks like the right tail is a little bit longer than the left tail. But as we get to larger and larger sample sizes, it starts to even out and looks quite bell-shaped and normally distributed. Questions or comments? Okay, so that was the breakout solutions. Those are now up on they're not yet in the zip file, but they are up as an individual file on GitHub if you want to grab that, and I'll update all those either at the end of the day today or sometime early this week. So we're going to shift to doing some graphics, and wherever Chris is, he's up for that. Yeah, that's it. All right, sorry about the delay. There we go. Cool. All right, guys. Chris again, other Chris. I'm back again for more useful things this time. I like to think.
What I talked about was useful?
No, that's not what I'm saying. This is actually a serious comment. So the things that I was presenting yesterday, as well as the things that we're going to be going over today, probably appeal more to the applied types, but they're good to know for all folks out here. I'm the applied one in this boot camp. So we're going to be going over some graphics today, and this is going to be a pretty quick module, but with just a couple of really simple slides, we're going to be able to get you guys going at a pretty high level of proficiency with a couple of these new advanced graphing packages that have been introduced of late. So this is sort of what we've seen already up to this point. We've seen some basic commands for histograms and adding certain lines, and this should be pretty sort of old hat to you guys at this point. Chris has been doing them intermittently throughout his previous presentations. The syntax is pretty simple, and you can make graphs they're nice, but they're not that great. They're kind of boring, and sometimes.
So what I do is not useful and it's kind of boring.
No.
Point taken.
Not at all. No. We're just trying to take all this incredible stuff that has come before these slides and make it a little bit sexier.
Yeah, I'm not sexy.
It's comparative. I said sexier. Yeah. So for the moment, we're going to sort of go out with the old here. Now I want to show you guys some just an example to see what I actually mean by sexier. Because you could have something like this, kind of blah. It's got a red line. All right, that's great. But then you have things like this, right? And so this actually has a very practical purpose, right? Each one of these panels right here, obviously you have your X values and your Y values. You don't need to know what those are. You don't need to know what this is. But basically, this is a graph that shows what happens to these parameter estimates for a thing you don't need to know about. But as you introduce measurement error into those parameters, so you can see here is the. What's that?
It's not working.
What do you mean it's not?
Oh, now I see.
Oh, look at this. Yeah, I'm not a physicist here. Okay, so you can see this is with no measurement error. This is with a little bit of measurement error, a little bit more, and a whole lot of measurement error. And we basically use the various aesthetics that are available to us in this cool package called ggplot to show how these how your results could be changed, how they could be corrupted based upon changes in your underlying parameters. So we've basically gone from graphs that are simple, practical, probably what you would use if you were just doing, trying to get an idea of the data for your own work. But then once you've come up with these amazing results and you want to publish them and show them to people and get them to take you very, very seriously, you can come up with really cool things like this. And there's another one here as well for the statistics folks. If you were interested, say, in looking at how the consistency of your OLS estimators changes based upon sample size, you can come up with something kind of cool like this. You see again down here, this is the number of cases that you're going to be looking at. And you can see here what I've done is I've taken this color scale, and this is the standard deviation of a normal distribution, standard normal distribution that you're drawing from. And you can use this extra aesthetic here, this color gradient, to basically add another level of change, another dimension of variation onto your plots. Not that you can't do these things with the base R graphics.
It requires some hurdles. The output isn't always the best. And really, writing things like this, especially using the very practical packages that we learned yesterday with Plier and Reshape, they all interface with these new things like ggplot, which make this incredibly easy to do, such that you probably won't even need to use the base R graphics anymore. So, now that we've gotten that bluster out of the way, let's move on to how you actually do this. So, aside from base R graphics, there's really two main competing packages that people tend to use if they're going to do some sort of higher level graphics work in R. One is called Lattice. This is developed by Deepai and Sarkar at ISI Delhi. And the other one, which is, it's probably a little bit more prominent, it's also a little bit cult-like, is the ggplot2 community, I'll even say. And so my idea with this, I don't want to really try and show my affiliations in terms of which packages I like better. So what I'm going to do is I'm going to show you guys how to make a variety of different plots using the syntaxes for each one of these different programs here. So you'll see what the basic output looks like, and you can decide which ones you like better. And this way you'll know how to do them all. And eventually when you do realize that ggplot is better, you can just go ahead and go with that. So some background here. They're both built on this package called Grid. I'm going to be extremely forthright in saying I have very little conception of what Grid actually does, but I'm told it's important. So just if someone asks you, what's this built on, you can say Grid. And the other thing is they're extremely complex. These packages there's a lot of time has gone into developing them, and there's a ton of options and a ton of different ways to customize them, such that each one of the package authors has literally written books on just how to use these particular packages. This is the sort of thing that cannot be contained in a simple help file. This needs 200 to 300 pages of exposition to actually give you the full range in which these different packages can be used. So, Lattice versus ggplot. First of all, a couple of things that you might be interested in as to why one initially might be drawn to Lattice over ggplot to begin with. So Lattice is it's a little bit faster. There was a handful of guys who liked testing out different packages in R, and they actually did some comparisons to see between Lattice and between ggplot which one's faster if you're doing a whole lot of plots in succession. And it turns out that Lattice is a bit faster, but again, this is the sort of thing you're going to have to running functions that are requiring you to graph very, very large underlying vectors and data frames, and you're going to have to be doing this many, many thousands of times to really see the difference. However, when you get to that space, Lattice is a little bit quicker in terms of generating the actual graphs. And again, sort of starting up, Lattice is a little bit simpler. We'll see this when we get more to the syntax. It's easier to get going, if you're just starting out with Lattice. Although once you understand sort of the basic language of ggplot, the differences are sort of minimal. The other thing which we'll see is Lattice is it's significantly better at doing these things called trellis plots, which are sort of a graphical analog to what we were doing yesterday with the split, apply, combine strategy. Where we take some data frame, for example, split it up into smaller data frames on the basis of the values of some variable, and then apply some function. The idea behind trellis graphs is you do the same steps, you split, but instead of applying a certain function, you're just going to be applying a sort of graph. So if I had 10 different values of this one variable that I was interested in using as a split, I would get 10 different graphs of whatever relationship I was looking at. Lattice, you'll see in the syntax, it's sort of built to give you these sorts of graphs which really do sort of split apart your data and represent the relationships graphically. So Lattice is very, very good for that. And the other thing is it's able to do three-dimensional graphs, and I mean this in the most conventional sense possible. If you want to have a cube of some sort that has some sort of line moving in 3 dimensions, you can do that in Lattice. You can't do that in ggplot, although those sorts of three-dimensional graphs are probably not the best way to represent your data, especially if you can't animate them and if you can't turn them around. Lattice is still going to give you, what is essentially a stable 2-dimensional figure just rendered in 3 dimensions. We'll see that in a second. But if you're really into that sort of thing, you're going to want to use Lattice. So a couple of things about ggplot. it's generally, it's a little bit more elegant, it's a little bit more put together. Again, this is just the sort of thing, you'll know it when you see it. I don't really have like an actual explanation for this, but ggplot graphics, without having to customize them a lot, they just look a little bit cleaner, a little bit nicer. But again, I think this is a question mostly of personal taste. The syntax is a bit more logical, which makes it easy once you figure out the basic idea of what's going on. It's easy to sort of get up to a fairly sophisticated level quite quickly. Whereas if you pull down a help menu for the lattice graphics, you'll see that there's your basic formula commands that you're going to put in to say which variables you want to graph where, but then there's, I don't know, somewhere around 1 billion different parameters that you could specify, and they're not grouped in any super logical order. You just sort of have to know where they are, and I'm sure after you use it for a long time it would become sort of second nature, but there's definitely a big barrier to entry there. ggplot is a lot better at sort of grouping naturally, not creating these trellis plots where you actually have separate plots for each subset of a variable. ggplot is excellent at saying, all right, I'm going to give you one variable and I'm going to graph, say, a number of the same lines on the same plot, but those lines are going to be sort of delineated on the basis of the values of some variable. We'll see this is where ggplot intersects really well with the melt command that we learned yesterday, where we could take this big data frame and basically collapse it into a column that is your identifier variable and a column that represents whatever, basically the definition of the value that you're interested in, and then the value itself. You could feed a data set like that into a ggplot graph and just say, all right, I want you to graph, say, line graphs for each different unique value in this characteristic identifier, and it'll automatically do it. You don't have to specify, I want you to graph country A, country B, country C, and not this one. It'll just do everything automatically. And the other thing is, which is really, really cool, I don't know I don't know how many of you guys have tried to do anything with GIS, but it can be a little bit annoying, and the maps that you get, again, they don't look that great. Within the last 2 years, the guy who's developing ggplot has teamed up with this other guy to basically take the contour function, which we'll see in a second, and apply it such that you can more or less download a Google map, get some geocoding for whatever data you're looking with, and overlay that contour data right onto a map. So if you're interested in doing something like, I don't know, mapping out crime statistics for Berkeley, what you could do is very simple thing, say, all right, I want to go to Google Maps, get the geocode of a map of Berkeley, and then I'm going to take some other data that I have which shows sort of crime rates based upon latitude and longitude. And again, with the same syntactical approach, ggplot will allow you, with this thing called ggmaps, to overlay that data directly onto the map. So you don't have to worry about any of the very serious first-hand complications for doing GIS work. Unfortunately, I'm not going to show you that today because it doesn't really do so well with RStudio right now. You'd have to run it, at least I've had to run it when I've done it myself, outside of RStudio. So first, some data, just some background on the data that we're actually going to be working with here. It comes from the Comparative Political Data Set 1, which is this big, huge data set of, it's a cross-sectional time series, it's panel data, and political scientists really, really love it because it's got data on just about everything. I've sort of given us a little bit of a snippet here that has the year, the country of interest. V-turn is a measurement of voter turnout in a given election. If you guys play around with the data, you'll see it looks a little lumpy. You'll have basically a series of lines, and then it'll jump, and then another series of lines. Just so you know, this is because countries don't have elections every single year, and what they've done in this data is assume that this is the constant voter turnout for all these years. It avoids some missing value issues too, which is helpful. Outlays is just how much the government is spending. This one over here, real GDP is real GDP growth, and unemp is the unemployment rate. So we're going to play around with a couple of these things to show you some example graphics. So, first thing, I want to go over the basic usage, the basic syntax of each one of these graphing programs here. So we'll start with Lattice. And the basic call for doing graphics in Lattice looks a little something like this. You'll have graph type. Again, it doesn't always look like this. This is just sort of a stand-in here. but this is going to indicate what sort of graph you want to do. This could be an XY scatter plot, a line plot, a contour plot, an image plot, a box plot, that sort of thing. If you're looking for a particular kind of graph, you're going to want to look for the function that starts with that name of the graph. And then within each function here, you're going to have to enter some sort of formula, which we'll cover here in a second. You enter your data set, and then after this comma, there's a whole slew of options, as I said, that you can put in. This includes, labeling, doing limits on certain axes, your color options, and other stylistic things. The list is very long. So a little bit about the formula aspect here for lattice. So I've given you a couple examples of the basic formula usage for lattice graphing. The thing to be careful about, and one thing which makes ggplot perhaps more preferable, is that although it's pretty much similar for all your different graphs, how you actually need to specify the formula is a little bit graph dependent, especially if you want to do things like 3D cloud plots, certain things with box plots. You're going to need to go to the help file to look specifically for the formula that they're looking for. However, we can sort of distill some basic ideas. So the first one in here is if we were to just enter x in our formula, x here is just a stand-in for whatever variable we were interested in. Say we wanted to do a histogram or something like that. That's all you need to enter if you want to do if you want to make some sort of distributional plot, like a histogram. So that's pretty simple. Now, if you want to do something that shows the relationship between a variable and some other variable, let's just consider the case for two variables here. You basically enter this formula as x tilde y, and that's really all you need to do. It's pretty simple, and it's very analogous to the sort of the LM and GLM context that we've been seeing before. Now, this is where lattice gets kind of interesting, and this is sort of my inspiration for saying why lattice is sort of built for doing trellis graphs, the plot analog to the split apply combined stuff. It basically, using this conditional operator here, you can tell lattice, all right, I'm interested in this XY relationship. However, what I also want to see is how this XY relationship varies conditional upon the various values of A. So if I wanted to see what was the relationship between voter turnout and outlays conditional upon different variables of GDP growth, I might write, okay, voter turnout, outlays, conditional GDP growth. And what that will do is it'll say, for each individual plot in these trellis graphs, it'll graph the relationship between turnout and outlays, and then for each different value of GDP growth, it'll graph another subgraph. You might not want to do that because you could have a huge amount of unique values for something like real GDP growth, but it illustrates the basic idea.
So Chris, I'm guessing that just for mnemonically that the thing on the left side is actually on the y-axis?
Yes.
Okay, so you might think of this as y tilde x instead of x tilde y.
Yeah, and you guys can play around and see, depending upon what you want to show. It's pretty flexible. And there's sort of two other conditional things here. Again, these are sort of related to what we had seen with GLM and LM. So x tilde y conditional on A and B. That's basically, it'll create conditional trellis graphs for all the joint combined values of A and B. This is sort of the same idea of the interaction operators that we saw yesterday with the LM and GLM package. And finally, if you did want to do something in 3 dimensions, you can basically specify a z variable specifically, and specifically first, followed by a tilde, and then the interactions between your y variable and your x variable. Now that's only for doing graphs that are going to need 3 dimensions that can't be metered out by trellis. Yeah?
Is A or B the length of X, or is it just the unique values that you're conditioning?
It's really just the unique values. It could be the length if the length is the same, if the length of your vector is the same as the length of the vector of unique values, yeah. But in general, it's really just, it's as if you were to write X relationship Y conditional on unique some other vector.
Well, wait, I think, maybe I'm misunderstanding. I think what it is if you've got a data frame, you're going to have a Y variable, an X variable, and then an A variable. Is that right?
Yeah.
Okay. So there are going to be repeats in here in the A column. Yeah.
Does that make sense? Okay. So this is the basic syntax for lattice plots, and these are the formula relationships that you're going to need to know about. So let's see here. Oop. So now the basic usage of ggplot. So like I said, it's a little bit more complicated at first, but once you sort of start to play around with the graphs, you'll see how the parts are all sort of working together here. So the basic plot, the basic call starts off not with calling the particular type of graph that you're interested in, but you just have to make a sort of broad level call to the ggplot function itself. So you start with ggplot. Similarly, again, you specify some sort of data set that you're interested in. And then you need to specify these things called aesthetics. I'm going to talk a little bit more about those in a second, but the basic idea behind aesthetics is that this is the section of the call which is going to tell ggplot, all right, I have variation on these sorts of things, and I want to represent that variation on the basis of these sorts of capabilities. And by capabilities, I mean I want this variable to be my x variable, I want the values of this variable to be my y values, I want the values of this variable to say represent, I don't know, the color that I'm going to assign to a particular point, or the shape, or even the size, depending upon what sort of pointillage that you actually use. It's a pretty big category, and I'll explain a little bit more, but this is sort of the workhorse of where you're going to be indicating what sort of relationships you actually want to show. And there are certain options which you can put within this aesthetic parameter, and there's more options. You can see if you go to, so Hadley Wickham is the creator of this, of ggplot, and if you go to his website, actually if you go to the website ggplot2.org, there's a very, very detailed help file there which will show you basically all the options that you would add onto this, onto one particular call. And it's huge, and I'm not going to go over them because it gets kind of tricky very fast, but it's very well documented if you want to start getting into higher level options. So another thing to note with ggplot, which is a little bit different than Lattice, Lattice likes everything to be contained within one call. Everything you're interested in doing, you basically, once you call that type of graph and put in your left parentheses, everything that you're interested in putting on that graph more or less has to be contained. Is there a question? Everything that you want to put in that graph has to basically come before you close out with that right parentheses. ggplot works a little bit differently. It sort of works on a layering foundation. The idea is you put down some base layer of graphics, and then with subsequent terms that you're going to put in these calls, you're going to put different types of data with different types of aesthetics onto the data that you've already plotted. So that's why if you see here, if we follow the parentheses out here, we've got this call to ggplot, right? We've got our initial specification of data, some initial specification of the aesthetics, right? And this is really our closed parentheses. If this were Lattice, and you put this plus sign here with these more specifications, it would return some nasty error message. But ggplot doesn't work that way. We've got basically a standalone command right here, which if we only evaluated this ggplot thing, it would, well, technically it wouldn't give you anything. You'd need this other aesthetic here, which I'll talk about in a minute. But what we're doing basically is adding basically another graph right on top of the existing graph that we're already working with. So to just give you a graphical example of how this works, so take a look at this call right here. Basically what I'm saying is I want a graph within my data. I want to see the relationship for voter turnout and real GDP growth, and I want to display that. Again, we'll go over these more, but I want to display it as a point, and I want to make those points black. So that's my basic thing that I'm trying to graph, right? And now say I wanted to add another layer on top of that. This time, I also want to do points. I want to use the same data set, which is my data, but now I want to graph voter turnout against unemployment, and this time I want the data points to be red. So this is the resulting graph that you'll get right here. You can see this is voter turnout. This only specifies the first aesthetic call here, but you can see the black points underneath are the first relationship we tried to graph. The red points on top are the second relationship. Now to see how ggplot does this layering, what I've done in the next call is basically flip these colors. So I want this first data that I'm putting up here to be red in this case down here, and I want the second one now to be black. And you can see how the graph changes. It's the same data, except we've sort of switched the coloring around. And if you probably can't see this on the screen, but if you look up on the slides, you can actually see when you get some points that kind of overlap, you can see there literally actually is an overlap between the points. So this is the basic ggplot philosophy. You create a basic graph, and then you add subsequent sort of additional data sets, or you tweak your style parameters as you go. Question?
Sorry, maybe this is straightforward, but maybe with the genome point, I don't understand how that function can be first with only the argument colored red and it without all of the rest of the
Right.
data, my data, aesthetics.
Right. So yes, there's one other thing I should say here in explaining this. So your first layer that you apply, you have to call ggplot, right, with this first aesthetic, and then before we'll actually graph something, you actually have to specify the point style or the line type. You have to say what kind of graph it's going to be. And so really, I could have for this initial graph just said ggplot data, my data, aesthetic, X voter turnout, Y real GDP growth, and literally just put G on point and then just 2 empty parentheses. And that would give me that first point thing. Now that's the only time in a multi-layered ggplot code that you're going to have to enter the call to ggplot and then this particular aesthetic. Again, I know aesthetics is probably, you have very little idea of what that is. I'll explain that in a second. But that's the only time you're going to have to proceed in that way. All other layers, all you have to do is call that aesthetic directly. So you see here, when I added the second layer, I didn't have to say, all right, ggplot again, and then geonplot again. I literally just went straight to geonplot, and then just referenced whatever data I wanted to use. Does that make sense? Yeah.
This might be kind of the same question, but like, how come the color equals black isn't part of the ggplot call? Or like the,
Again, it's specifics to that first call. You can sort of think of it like anything that you might put in the first call over here is going to be outside of this aesthetic parameter in a subsequent call. I mean, I don't know if there's any rhyme or reason for it. It's just to make it work. That's how the guy has set it up. Yeah.
And basically, if you want to do a different type of graph, instead of G on point, you can make that a bar graph or something like that. So then you'd have, instead of the second G on point, you can have that be bar or whatever.
So in theory, you can do that. There are some built-in rules to prevent you from doing silly things like trying to overlay a bar plot and a point plot, for instance. But that's the basic idea. Like if instead I wanted to put some sort of line plot, I would call the geometry geom line. I'll give you some example of those in a second, but yeah, that's the basic idea. Yeah. Any more questions on this before I go? Yeah.
Is it a way to know what are the XXXX arguments can be? There's a list or something?
Yeah. If you go to ggplot2.org, there's a huge list. It's literally he's got at least, I'd say, 20 or 25 geometries on there. They're pretty sensible if you think about it. Like if you want to have a line graph, you're going to put geom line. If you want something that has points, you're going to put geom point. If you're going to do a contour graph, you're going to put geom contour. Again, we'll see that in a second. I'm going to go through some specific examples, but this is just to get you guys familiar with the very basic call. Okay? So yeah?
And in geom point, these are the 3 things that we are supposed to put for sure or something like that. I mean, these are 3 basic parameters we have to put, like data, AES, and
Yeah.
or something like that.
Yeah, you basically have to say, all right, ggplot, here's the data source that I want you to work with, and then here's what I want to see. So that's the my data call, and then it's the X and the Y. Or obviously, of course, if it's just a histogram or something like that, you'd only need to specify the X. But again, the syntax for that, it's specific to the aesthetic argument, which we'll see literally, I think, in a second. Okay.
There's a question back here, Chris.
Sure.
My question is about like labels. So it kind of seems like when you do the first ggplot call, you're kind of setting up your grid, and then you layer on what kinds of points and lines that you want. So if you want like an x-axis label and a y-axis label and a main label, that goes in like the ggplot options,
Yep.
not in like a geom.
Yes, and we will see this. I'm glad that you guys are excited, but I want to go slowly here so we build this up. Are there any other questions before we move on to specific? Yes.
So is the set of points specified second, does that cover up the first set? I'm wondering if there's a way to show some points translucent if there's some in the same spot.
So if you look at the slides, let me see if I can find one for you here. Yeah, I mean you can see a couple of them if you just sort of look in this mass right here, right? Pick out something that sort of looks slightly concealed, right? And then go look at it at the bottom graph. Yeah, the red is generally on top on the second one, and the black is on top on the first one, because the first thing that we graphed was black in the first one, and then it was red in the second one. So you're going to have the black points underneath the red points. I don't think I'm going to really be able to point something out for you here too much, but it's probably easier to see on your screen. Oh, is there a way to actually change it?
To set the transparency.
Oh, yes, there is. But it would take more than the time I have here. It's in one of those options. Once you can actually specify the different translucencies of all the colors. That's why I say these things are infinitely customizable, and that's why they require books as user manuals. But yeah, you can do it. ggplot.org.2 is a great resource for this. Okay, one more question call. All right, so let's see some basic examples of how we would do the same sort of plot in both lattice and ggplot. So you're coming to this data set sort of fresh, and you want to get an idea. All right, what's the distribution of some variables? The first graph you might want to make for a handful of things is a simple histogram. You want to get the idea what's the density of this variable. So if you want to do that in lattice, again, we know we want sort of a density graph, so we have to be thinking what sort of function am I want to call? Something that has density in the title. And you see they have one right here called density plot. Okay, and here's our formula right here. Basically, we only had to specify the variable that we were interested in, and in this case, this was voter turnout. We specified the data that we were interested in. This comes from my data, and this is exactly what lattice will give you with this simple call. Again, this is sort of baseline assumptions for your titles, your limits, and your colorings, and all these things. This is what the package author decided would be the most basic output. So that's how you do it in lattice. Pretty simple, but again, thing to note here, you have to remember exactly what this function is. You have to remember, this is not very complicated, of course, but you have to remember exactly what the formula is, and the data stuff is not too bad. But then remember, there's a very, very large possible list of options to make the graphs different however you want. So if you want to do the same exact thing in ggplot, what you're going to do, again, as before, you're going to start with your call directly to ggplot. And the first thing you want to specify, it's very important to specify this, is the data that you're working with. So again, we just say data is going to be my data. And then with all ggplot sort of things, you have to specify some sort of base level of aesthetics. And in this case, we only really have one aesthetic that we're interested in that we know for sure, which is the values of, in this case, voter turnout. ggplot is going to actually do all the kernel density and calculate the other statistics, so you don't have to enter that. So you just say, my aesthetic in this case is, it's just the X, and it's my voter turnout value. Now, if we just entered that, ggplot would say, okay, that's great. So what do you really want me to do with this? I know you want something with this X here, but I'm not 100% sure. So you have to specify one more thing separated by this plus sign right here. And in this case, we want to specify our geometry to be density. So it knows now, okay, I've got this data, I know what variable you're interested in, and I'm going to try and coerce this into a density graph. And for the basic call, you don't need to put anything in this first bit right here, and this is what you'll get. Again, pretty similar. There's some sort of basic stylistic choices. See here, he's got sort of some pointillation to represent the actual coverage of the histogram. whereas this is just sort of a connected line in ggplot. Any questions on the histogram thing? Or the density thing, sorry. No? Okay. So, you do this for a couple variables, you know, you're starting to feel pretty comfortable with things. Now you want to actually get into analyzing relationships between these different variables. So in the lattice context, it's not referred to as a scatter plot per se, it's called an XY plot. Again, same exact thing. You know, the function that we're actually going to call, it's got to have something to do with the type of graph that we want to get. It's XY plot for lattice in this case. And what we're going to specify here is our Y variable first. This is our formula. So our Y variable here, it's going to be outlays. And then the X variable that we're interested in is going to be voter turnout. So basically what we're looking for here is any sort of relationship between the overall voter turnout in a particular year and whether or not that influences government spending in some way that we could discern graphically. And again, with the call to my data set here. And this is what you'll get. It's pretty straightforward. It'll just turn the labels into whatever the variable names are, and it's sort of default plotting pattern for points. In the XY plot for lattices, it's this blue color with the hollow circles. So this is what you get. Now, same exact thing, however, in this case, done with ggplot. Again, your first call is to ggplot. You specify your data, which is my data, and now our aesthetics, we don't just have this one variable that we're interested in. We're interested in how that variable relates to a second variable. So we have two aesthetics at this point. And the aesthetic here, our first one is going to be the X, and this is voter turnout. We say our Y is outlays. And now remember, that's not enough. We need to do one more step for ggplot and say, this is the type of graph I actually want to see. And for this, the sort of the naming is a little bit more specific to the actual type of shape that ggplot is going to put on this graph. So you want to call the function geom_point. And again, if you don't want to pass any more specifics to this particular instance, all you need to do is put the two parentheses there. And you'll get a graph that looks something like this. You'll notice ggplot has this sort of gray backing to all of its graphs done in a very basic level, and it also goes for circles, but it will fill them in and make them black. Again, you can make these graphs look pretty much exactly identical with the right specifications, but the baseline sort of stylistic choices are a little bit different. Any questions on the XY plot? No. Okay. So, now this is, when you want to get into line plots, I think it's going to become a little bit clearer sort of the different philosophies that these package authors were taking when they were actually trying to write this code. And so now suppose we didn't want to do XY, just simple scatter plots anymore, but we wanted to do a line plot, something that shows a time trend, for instance. So let's say, just for no apparent reason at all, that we were interested in how voter turnout in France changed since between 1960 and 2010. So we could do that just as a simple scatter plot, right? And you'd get a little something that looks like this when you call lattice. Same thing, XY plot. Here's the relationship we're interested in, our Y variable, our X variable, our data. And then in this case, lattice has a nice little function here where you can subset the data to show just one particular, the values for just one particular value of a certain variable. In this case, we're going to subset it such that the only country we're interested in is France. And you can see this is how voter turnout looks in France. Now, the same thing, this is sort of repetitive here, but this is how you would do it in ggplot. The call to ggplot, you can subset it in a very similar way. And
note that the subset here is actually using the subset function we saw yesterday embedded within the ggplot.
Right. Important to note.
No, it's not part of ggplot.
Exactly. And then we add our aesthetics here, which our X variable would be the year, the Y variable would be our voter turnout, and then we've got our pointal geometry that we want here. Again, same sort of thing. Now, if you wanted to move from this sort of graph to something where you would actually connect these lines, instead of just having points out here, the The way you would do it in Lattice would be to still operate through the XY plot, but instead now you're going to have to specify a type. And in this case, the type for a line plot is called L. And this is, again, this is just one of the very many options that's actually embedded within the whole call, which you would work with. So if we wanted a line plot of the same voter turnout data using Lattice, we would call it just like a generic XY plot, except we have to specify here that the type is going to be line. So we just type in type equal to character L. Again, in the documentation, which you can get really easily through RStudio, it lists all the potential values that these sort of parameters could take. Now, if you want to do that in ggplot sort of, it doesn't like to think, all right, I'm going to sort of graph something in 2 dimensions, and you need to say how I'm going to, what types of things those should be, and how you want to connect them. ggplot is much more focused on the overall sort of geometry of what you're interested in graphing. So in this case, we would no longer call geom point. In this case, we would make a call to geom line. Now notice everything is basically the same from the beginning of the call to ggplot up through the end of that initial call. The only thing we've changed is to say instead of calling geom point, we're going to call geom line. And this gives us the same sort of graph. It decides I don't want to do any points. I'm going to connect all these values with lines. So I guess this is sort of where the packages start to diverge in terms of their syntax. You see that basically this last item here where you have to specify the overall geometric aesthetic is basically how ggplot changes through these different sorts of shapes, whereas with XY plots and Lattice, it tends to do it more as a sort of an optional parameter within each one of the main calls. So are there any questions up to this point? Yeah?
Is the select just changing the name, or you don't actually change the name, or what is select?
Let's see here.
Select is part of the subset.
Yeah.
Because if you run without select, it gives you exactly.
Well, yeah, that's just because, yeah, you can. I think what I was doing there is I was just taking a smaller data set. I was saying, all right, I want to select on this the country being France, and the data set that I wanted you to give me back only had voter turnout and year. So you could still do it without having that particular select command. It's just going to be drawing from a bigger data set. I mean, you don't have to put it in there. I was probably doing something else with this in the background. So, any other questions on this before we move on? Okay. So a couple more types of plots here. Now, so I've been talking about trellis points forever, and this is what they actually look like. Okay, so say we were interested in the sort of the trend in voter turnouts over the 1960s, but we really wanted to see graphically how that changed in each individual country. So you remember from the syntax that we learned about how to work with Lattice, the way we do that is we write down our basic y-x relationship, but we write it conditional on whatever value we basically want to split up our data by. So what this is doing here is saying, all right, I want an XY plot, and I want to see the relationship between turnout and time, more or less, but I want you to make a small graph for every unique value of country. And again, the data is whatever we're working with. And this is what will come out. You can see Australia, where they have, criminally penalized mandatory voting is very, very high. Dropping off in Austria. Canada is kind of bleh. Portugal is really a sad state of affairs, etc. But you can see it'll basically split it up and combine it in a way that's it's pretty readable. It's pretty nice, and you can change the labeling on these things. You can change whether or not the scales are equal, whether or not they're going to be the same. Again, infinitely customizable. It's just the sort of thing you got to work through the options and live with it for a little while. But it's a pretty simple call. Again, it happens right here in the formula function. Now, this is why I say Lattice is a little bit better for these sorts of things, because when you try to do the same exact thing with ggplot, you've got to add one more sort of option code to the end. You can't just specify, all right, I would like a series of trellis plots within this aesthetic right here. ggplot doesn't really like that. But what you can do is add this option here, which is called facet wrap. And then all you have to specify here is basically the variable that you want to condition on. This is, in the previous example, this would be like our conditional country variable, except for the ggplot context, you have to say plus this function facet wrap and then country. And you can see it produces the same thing. The baseline default here, ggplot is going to sort of order things left to right and then going down based upon some sort of implicit ordering of whatever faceting variable you're interested in. In this case, it just sort of ordered our country names alphabetically and sort of went from A to Z, or U, I guess. Yeah, so any questions on this?
What's going on with the lattice ordering where you, like, it's like this weird draft bottom to top off? Is that just the order they were in?
The lattice wrapping? Yeah, so lattice has also done sort of an implicit ordering there, except it decided that U should come, it decided that A should come first and U should come last, but it was going to sort of build it from the bottom up.
Right.
Yeah, so again, you can change it. It's just, I just wanted to show you what your baseline output is going to be, for a simple call. Again, you could make these graphs look absolutely identical with no difference really, but it takes a series of sort of very heavy option manipulations. Does that explain why they look different? Okay.
Hey, Chris, in terms of
Yeah.
in terms of time, we do have some coffee and food out there. I'm not sure do you have a sense of how much longer it will take to go through the rest of this? Should we pause now or should we go to the end?
Let me just see. Maybe let's just do a little pause now. I want to say a little bit more about aesthetics, if that's all right.
Yeah, that
Okay.
works. Okay, so why don't we take a 10-minute break or so? There's some coffee and snacks outside, and then we'll pick up again. Do try. I think try. No, there is a slide. Yeah, so he's got a little bit here on creating JPEG and PDF, which I think I also sort of said yesterday. Yeah, so for creating graphics, this is basically it. There's not all that much to it. It's basically you're going to need to monkey with the sort of margins and font sizes and stuff like that, and then to produce it, you just basically wrap it in this call to a function and then the dev.off to close off the file. In terms of the tables.
So if you're interested in doing more than one model, say, and you want to get it into a nice journal format, something like that, the best package for that is TextReg.
TextReg?
TextReg.
Right.
Yeah.
TXRG.
Yeah, it's a little bit complicated at first, but basically, if you do xtab, basically you'll only get sort of a regression output where you'll have your estimate and then your standard errors and all that sort of thing. And it's hard to do multiple models as in like a journal format. But TextReg will actually, you can store each one of those results, assuming you've got your classes right, and then it'll produce a nice output table, which will rearrange, like put your standard errors underneath your estimates. It'll put in stars where it needs it. It's just a generally more customizable way to do table export. What's up?
Right, two things. One is like when you're talking about maps, so there is I'm sure you know that there's a library called Maps, and that's pretty. I mean, it's not like Google Maps or something hi-fi, but it's quite easy to use. If you want to mention that, and do you want to mention about the identify function because that's pretty cool, right? Like it pulls out the point data in the graph itself.
The identified function within what?
So if there's a not a histogram, it's like a scatter plot, and the identify function actually identifies each of the points. So if it's a country data, so it's like basically says a US, like in this plot it will say that which year it is, and people can individually see that which point it is and something like that.
Yeah. So are you talking about a specific function?
Yeah,
like
there's a
for
function
lattice?
there's a function called identify. I guess it's in lattice.
Yeah.
So that basically points out each of the points.
Yeah, so this is where it's difficult to do both these things side by side. So the ggplot philosophy, I guess, is that you should never label those sorts of things directly on the graph. So there is a way that you could put a label directly onto each one of those points.
Yeah.
But it's hard and it is ugly.
Okay.
So what he would do basically is say, have some sort of identifier variable already in your data, and code that information into an aesthetic, and then put a legend.
Oh.
So like, for example, like this.
Yeah.
It's the same idea. You could do the same thing. Actually, I do the same thing here with points.
Right.
Right?
Yeah.
So the idea is, he thinks you should never put sort of different country names and stuff in there because it just it interferes with the interpretability.
Yeah.
So you sort of would just say, you'll see here, the same idea as the identity variable is when you put when you specify which variable is going to give you the different shape values, it'll automatically produce this little legend over there.
Okay. Yeah, I guess it's I think that it's a more lattice thing that it allows you to like put the individual values on that graph.
Yeah. I mean, you can do it, but like in ggplot, right? You would have to. There's a text as labels function. Actually, and then there is another aesthetic called text, where you could read in a character variable and put it up there, but it looks gross.
No, it looks gross. It's just like sometimes it's good to.
Sometimes it's good, yeah. But I mean,
just to understand,
for a general audience.
Yeah. I'm sorry.
No, it's all right. I mean, I barely use lattice and I forget about all these things. So.
Okay.
Yeah.
Thanks.
Yeah. But let me ask you a question. What field are you in here?
What field?
Field.
Oh, I'm in School of Information.
Okay. All right. Graduate?
Yeah.
Okay. Yeah, because it's interesting. It's hard to market to a diverse audience like this, because sometimes the people that are more techie, they're more interested in different types of functions, like these contour things, whereas the social scientists don't want to get anywhere near contours.
Yeah, I honestly don't know much about that. I just spent some time in the summer to learn it, and I did some state, I think, before. But R is generally much better. I mean, you get tons of help in the community and all those things.
Yeah, state is just this like barren wasteland where if you can't figure it out, you're just kind of fucked.
Yeah, and it's like you don't need state. Like whatever you need, you have in R. And it's like if the performance is the issue, then it takes a bit of time.
But the thing is, it's not. It's if you know how to.
Yeah.
If you know how to write your code,
I'm
performance is not an
not so
issue.
good yet, so it takes a bit of time sometimes, or it takes a bit of time to figure out that which function, like, or these things I need to use.
Well, there is a high performance version of R that I think it's Revolution R or something like that puts out, and it's free for students.
Okay.
For graduate students at least, and they, it's like everything is written in automatic parallelization.
You're going to talk about parallelization a bit, right? I mean, there's a module or something.
I'm not Jared. Yeah.
Okay, someone is going to talk about. Yeah. I mean, because I'm taking this start like 154 and 215. So especially for 154, I'm not sure either Python or R. I'd like to stick to one platform rather than switching. And I'm trying to pick a big project and working a couple of class together or something like that. So if something is fast enough, like this Revolution I just mentioned, it's good enough. Like I don't need to, I need to go to Python to make the data set and then use R to do all the analysis. And it's much more easy to do it in the Yeah, thanks. Thank you for
Sure.
sharing.
Yeah. I hope it's been helpful.
Yeah, it is definitely. It's helping me sometimes to understand, like, so something I was working on in the summer, I was using this XY plot and all those things, but I had all those libraries installed already, and I had no very clear idea that it's coming from ggplot, it's coming from lattice, it's coming from something else, and now I'm like, okay, fine, so it's coming from lattice, and something like it's quite good.
Cool. I'm glad you like it.
Yeah.
Just a quick announcement, if you haven't marked off on those lines that you're here today in particular, not just yesterday, please do mark off that you're here.
Hours spent stressing. Let's start to reconvene. I have a timing question to pose to you guys. So in terms of, it looks like we're going a little bit longer this morning just as we did yesterday, so we'll have to sort of make up time this afternoon. There are two options basically. So Chris is going to finish up with the graphics, we'll have a breakout. At that point, we could either do a shorter session, which is, I would do the session 4, which is talking about packages, and we have sort of an early lunch, probably 12:15 or 12:30.
Or we could stick with the original schedule, which is to do Jared's session on scientific computing and workflows, which is going to be a longer session. In that case, we would probably not have lunch till around 1, maybe a little bit after 1. So can I get a show of hands of people who prefer the early lunch? And a show of hands for the late lunch? All right, I guess I'm going to have to do this again if I'm really going to be Democratic. Okay, early lunch? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Isn't there a function for this? 5, 6. All right, late lunch? 1, 2, 3, 4, 5, 6, 7. Basically a total tie.
Why did you avoid that?
Wait, what are the time? What did you say, Rob?
Early people might have real blood sugar
I think since we had a late break, I will cast a tie-breaking vote and say let's do a later lunch, realizing that we're essentially tied.
Okay. So, I hope by now you guys have gotten the basic idea of how you're going to sort of go back and forth between lattice and ggplot graphics. So just to show you very quickly a couple of other examples of plots that you could do. If you want to do contour plots in lattice, the function that you're going to call is actually contour plot. You can see here this is some volcano topographic data that we're actually dealing with here. You've got your basically your latitude, your longitude, or vice versa. I think I screwed that up. And then you can see it shows the level curves here for a handful of things. And it's the same idea. You have your z variable here, which you're calling, and you want to see the relationship for the z variable, each value of the z variable between the x variable and the y variable. And there's your call to your data. Pretty simple. If you want to do it in ggplot, same idea, except this time, you've got 3 aesthetics now that you have to worry about. So you're adding in this z, and then you just make a call to the geometry entitled contour. Same sort of idea. You can do the same thing with tile or image plots. It's called a level plot for lattice here. Similar type of call. Again, same with the data. This is what you get. That's the same exact volcano thing. And for ggplot, you just make a call to the syntax for this is a little bit different. So you need to add, in addition to the z-var here in the call to geom tile, you need to specify one more aesthetic, and that's for how it's going to sort of fill in these colors here. And then you just note that you want it to fill in the colors based upon the values of this z variable. Now that's just sort of a technical fix that you need to do to make the baseline ggplot graph look like the baseline ggplot, or the baseline graph of the level plot. But again, this is all really well documented in the materials for these types of plots. And here you go, just to show you really quick. This is the sort of traditional 3D plots that Lattice can come up with, and it can do them as a trellis as well. And the call for that is cloud. But you guys can see how this is done on the slides. So in the sake of time,
Please don't put a plot like that in your journal articles.
just saying you could do it, just for personal entertainment.
I didn't mean that as a criticism of you. I'm just
Yeah.
in
Yeah.
general, those are hard to view.
Unless you do like a series and you animate it and then publish it online. Okay, so now one of the really great things about ggplot, and probably the best thing for people who are doing social science, I'd say, is its ability to really, really easily take a data set and instead of producing trellis plots, produce a single plot with sort of different lines, different sets of points that somehow have a particular affiliation with a subset of your original data. So you remember yesterday when we saw the melt command, we would get our ID variable, sort of the placeholder for the name of our various variables that we had melted, and then you actually get the value. So ggplot can basically take our new data right here. We put in our data set, we specify our aesthetic axes here. We're going to have the year, we're going to have voter turnout, and then what we do is we say in this initial aesthetic right here, we want the color aesthetic to be of some importance in differentiating amongst our data. And so if you just put this call here with just an equal sign and nothing there, basically the effect is it takes away a silly label which looks kind of funny there sometimes. But then you make your call to your geom line, and within this geom line, you make one other reference to the aesthetic, and you say that you want your the color of your graphs to change based upon the values of the variable country, for instance. And what that will do is it will make a graph which looks something like this. You see it's got a series of line points, but what it's done, it's gone ahead and assigned a different color to each one of the different lines that corresponds to a particular country. So you can see you've got Greece here in red, Ireland in green, Portugal in blue, and Spain in purple. And so this is a really easy way to sort of do, not sort of trellis differentiation, but sort of differentiating between different unique values on a single group. This is very helpful for lots of stuff using panel data with countries and years.
I'm guessing, although I don't know for sure, that the data within country need to be ordered by the x variable so that the line plot can just connect dots. Although I don't know if that's true.
It normally will order it for you somehow using it'll make a call to arrange, as we learned yesterday, and we'll get it all set up for you this way. So, but that happens in the background. So this is where the concept of aesthetics, aside from just your x variable and your y variable, become very important, because now we're no longer limited to more or less 2 dimensions, and if we split it up in sort of an array format, 3 dimensions. Now we can also show how the values of these variables changed using differences in color, differences in the type of points, like the actual geometries, and differences in the size of each one of those different geometries. So we've got 3 basic aesthetics that we're going to be working with ggplot. And again, they all work in the same way, where you basically say which aesthetic you want to work with here in your overall call to ggplot, and then specify which variable you want to use, which variable you want to break up using that aesthetic. So here, right, we've used color, and so it's broken our line plot up on the basis of color. But you can see in a different call here, we're still interested in line, but we don't want to represent the differences between these countries using color. We want to actually use different types of lines. So what we say here is we're not interested in the color. We're going to break it up in terms of line type. And then over here on the side, we specify that the actual line type is going to be dependent upon the unique values in country. And so you see here you get this thing with a whole bunch of different lines. Some aesthetics are better for different lengths of unique vectors. For example, line type and shape sort of run out pretty quickly. Color, you can, well, this is a breakout question, but you'll see in a second. What's up?
So I just played around with that, and you put equal legend, or you can type in frog, whatever you want. It goes above the Greece, Ireland, Portugal, and Spain.
Yeah.
So it's that's just the legend now.
Yeah, this is exactly a legend.
Yeah.
It's just, it makes your graphs look better, because if I had some really wacky variable title name like country.mycleandat.var or whatever,
Right.
and I would use that to signal it behind the scenes, but then in this label right here it would say, oh, this is for each of the values of country.blah blah blah, whereas this just makes it a little bit cleaner. It's just sort of a workaround. So you can do that for line type. You can do the same thing for the shape of the points. Again, identical syntax, except you're saying shape, and you're specifying how you want to change that shape. And you can see it gives you a series of circles and squares, triangles, etc. And let's see here. Forget exactly what I was trying to do in this particular plot. But the other thing is here you can actually combine multiple aesthetics on one plot. And this is sort of, it gets a little complicated, especially when you're worried about interpretation issues. But say you had some x variable that you were interested in and a y variable, but then you also had a z and maybe a z prime or something like that you wanted to illustrate. You can, again, apply multiple aesthetics to the same graph, and the way you do it is really just to specify those aesthetics. Again, we're saying here we're going to do something with the color aesthetic, we're going to do something with the size aesthetic, and then we specify here, all right, we want to change our points, the color of our points based upon the value of country, and we want to change the size of the points based upon real GDP growth in that particular year. So what the resulting graph gives us is basically for every year what the voter turnout was, what country we're dealing with, and what the value of their real GDP growth was, all in a single point with 4 different combined aesthetics. And it'll give you legends for each one of the different aesthetics. Obviously, it'll tell you these are the countries, and this will tell you the magnitudes of of real GDP growth. If you feed in a continuous variable, the legend will sort of bin it off at sort of ways that are selected for with some fancy background calculations. But you can obviously change the binning of these legends. Again, it's one of the infinite options.
So being old and boring, I will admit this is pretty cool.
Right. Thank you. So let's see. Is there a reason why? Okay. So this gets back to sort of ggplot works on this idea of the grammar of graphics. And so I say if you read about it, it's really a philosophical package. And we've been talking about aesthetics, but basically I just want to spell out for you. Oh, yeah.
In the previous slide, the way you subset the data set, in the first line, like subset and then take the data set and then do another subset. So is there any specific reason of doing that? Because we did it separately for the overnight problem we had for John and Kerry and Bush, and I think we can do the same way here as well, right?
Yeah, I don't see why not. I mean,
yeah, I was asking that is there any specific reason that you did another subset within or something?
no, I was just feeling like doing that when I wrote this piece of code, you know? Yeah, there's no hard reason, yeah.
So is the main reason to put the color equals country in the, I guess, the layer call set varying different things in each layer? So notice that you put it in the ggplot call, it does basically the same thing.
Sort of. I mean, because it could get more complicated. Imagine if you had a line plot, right? And you wanted to change the aesthetics of that line. Say you wanted to change the shape, right? But then you also wanted to overlay a different layer, which was just going to be points, and that you wanted to specify with color. In that case, you would have to basically break it up and say, all right, I want the aesthetic in my call to geom line to be, what did I say, shape, and then you'd have to say, plus the geometry of the points, the other layer that I'm going to put in, and then you have to also specify that the aesthetic for that point, for those points, is going to change on the basis of whatever the color was. You mentioned that in its particular layer all the way at the end.
Right, okay.
Does that make sense? Okay. Anything else?
In the last plot that you showed, is it like here the legends, the size is like, it's all across the data set, right? It's not like specific to some.
It's for whatever I put in this subsetted data here.
Yeah, so I was asking, like, is it possible to make it like within that country or something, like the biggest one will be the biggest one, like that sort of alteration?
I mean, yeah, the easiest way to do that would just be to do it on a smaller subset of data to begin with. Because, I mean, if you did an expansion like that, you would have, I don't know, 30 legends. Yeah, so it's just, you can do it, but it's going to look weird. Anything else? Okay, so moving right along onto the grammar of graphics here. I just want to say a little bit more about sort of this aesthetic call, just to make it totally clear. And what the entire idea of these aesthetics are working on is that there's a whole, if you want to represent something graphically, there's a series of requirements that you need to build into each one of these. So the first thing that we need are one or more statistics, and these are very common to us. You have some sort of mean, an identity, a median, a mode, some sort of numerical value that we can pin to a particular well-identified point. Then what you need is a coordinate system, and this is basically a way for showing interactions of these different, basically the resulting statistic that happens from a geometrical interaction between various underlying variables. And then once we have those coordinates represented with some sort of coordinate system, we want to basically change two things. One are the geometries, and one are the scales. Basically, geometries are very good for representing things that differ in terms of kind, things that are difficult to order, and then we have scales. And these are the things that we can order pretty well. Now, part of the breakout problem is going to get you to think about what sort of aesthetics ggplot has at its disposal can actually be used as geometries or scales or geometries and scales. So just have this in the back of your mind when you're toying around with these examples. And so this is just so we're absolutely clear here, these are the basic options that you're going to need for your aesthetics in ggplot. You've got your call to your color, some sort of call to shape. If you're doing a line graph, you need to call line type. If you're doing a point graph, you need to call shape, and then you can call to size. So is everyone pretty clear on how we go about changing these aesthetics? Okay. Now, everyone always wants to know about useful things like titles and labels and limits and things like that. Again, they're a little bit specific to each one of these things here. So this is just the XY plot that we had been doing before in Lattice. And you see if I want to put the title in, it looks, the particular parameters that you call are the exact same, I think, as when you use base R plots. So you call ylab, and you can say this is my label. Same thing for xlab. If you want to get a title on the graph, you call main, and you can sort of change the overall lengths of your different axes by calling to xlim and ylim. So again, these are really well documented, but these are the basics that you're going to need to know for having some sort of useful graph that you can produce.
And if you do want help on that, that's where the help on the par function, PAR, is useful.
Yeah, exactly. And it's very, very similar in ggplot, a little bit different. You call xlab, and xlab again is like its own layer. It's not like an option, it's like you actually have to go up to this graph that you made already and tack on a different x label. So you're going to call xlab, and just it only has one argument. I just put it out here so you can see it. And you say your x label. Same thing with ylab. One difference here is they don't have a call to main to put a title up on the entire graph. To do it in ggplot, you have to call ggtitle for whatever reason, and it'll put a title on the graph there. So those are the most basic things that you're going to need to know in terms of sort of options, I guess, at this point. Now, Chris talked a little bit about combining many plots, and you've seen this already using the par function. This is just an example that I had, so I'm not going to go into this too much. The issue is because lattice graphs and ggplot graphs are built on the grid, on this grid package, if you want to take them and combine them into some sort of table of graphs, using that par option isn't exactly going to work. You have to use a function which comes in the grid extra package called grid arrange. The easiest way to do this, I've shown you an example here with ggplot, is to say I've got 3 plots, and the easiest way is to take these ggplots and store them as an object of some sort. So we have plot 1, and we're storing ggplot up there, whatever this one is. Same thing with 2 and 3. And then you just make a call to grid arrange, and you simply list all these different objects that you want to sort of cram into one bigger image, and then you just specify how you want to sort of arrange these in terms of the number of columns you want to have and the number of rows you want to have. And the call to grid arrange will give you something like this that you can actually work with. And you can see if you try and use the par function to actually do this with a lattice graph or a ggplot, it'll do something like really just give you only the last graph that you made. It won't combine them into a nice little table of graphs. And then the last thing, once you've made all these cool graphs, you probably want to know how to get them out somewhere. So there's 2 basic image types, and I'm going to admit that I am completely unexpert in these different types. Basically, the idea is if you want an image that's going to resize very well and maintain quality, you want to save it as a PDF or some sort or a PostScript. These are called vector images. But if you want something like a JPEG, which doesn't resize so well, but I don't know, for some reason maybe better in certain contexts,
it's going to be smaller in cases where a PDF might be huge in some cases.
Right. Yeah, so size over quality sort of thing. You can just call JPEG or PNG. And it's pretty simple. You've seen the syntax already, where you just say what sort of file you actually want to save. You specify the width, you specify the height, you do your plotting, and then you run this dev off command. Same exact thing for doing vector images. And this will also work with your lattice graphs. ggplot has its own sort of save function built in called ggsave. Similar syntax. You enter the file name where you want to save it. You enter the plot that you're interested in saving, and you have your width and your height options, but you also have a scale option if you don't actually want to change the dimensions of it at all. Relatively speaking, you just want to make one that's bigger or smaller. You can enter a scaling parameter too, which will change how big the actual image is.
So is there's an option somewhere in that says what kind of file format you want, presumably?
Yeah, all you need to do actually is if you want to save it as a PDF, you put file name mygraph.pdf.
Oh, it's actually interpreting the...
Yeah, it'll do some interpretation there, and you can save it as PDF, JPEG, any vector, so that sort of thing. Yeah?
Where is grid range? I don't seem to have it loaded.
Grid arrange is in the grid extra package. Okay, so the breakout. I'll do this real quick here. It's a two-part breakout. So the first one is, as I mentioned, not all variable types are suitable for representation by every ggplot aesthetic or any aesthetic in general. So see if you can come up with what kinds of variables, and I'm thinking in terms of discrete or continuous, ordinal versus non-ordinal. What kinds of those variables can the aesthetics color, size, and shape meaningfully represent? So that's the first breakout question. And the second breakout question is, ggplot, we know that it does layers really well, but it also lets you do a whole lot of statistics that you can add as layers. So what I want you to try and do is see if you can fit a simple linear trend line to every facet of the gridded voter turnout graph that we produced just a minute ago. And the hint here is you want to consult the help file for geom smooth. So I think that is about it. Are there any questions before we get going on the breakout?
You don't have to go over this, but could you point me to, for the lattice, you have the CEX function for like changing the sizes of things, and also the spacing of the Y label away from the blind access. How do you manipulate that with ggplot? I'm not going to be able to recall the specific argument off the top of my head, but it's if you go to the ggplot documentation on Hadley's website, it'll be there. Okay.
Yeah. Okay. I think breakout time then. Cool. Okay, so can anyone sort of offer up an answer for the first breakout question here? What sorts of variables can we actually use for what sorts of aesthetics? Anyone want to volunteer some sort of answer? Anybody? Bueller? Well, yeah. I've been authorized to give these out, so. All right. Well, then I will give myself a piece of candy here and tell you guys what's going on. So, the basic quick answer, which you need to know, is that for ggplot, this is what you can represent with the different aesthetics. You can use color to represent variables that are inherently continuous, discrete, ordered, or unordered. And the reason is because when you're dealing with the color spectrum, it's got a natural ordering to it. But you could also break it up and take random pieces that are explicitly unordered to demarcate your variable. So that allows you to use the color aesthetic to represent variation in variables that is discrete, continuous, ordered, or unordered. The same is true for size, obviously. Size is probably a little bit more obviously, a little bit better place for discrete and continuous, but if you think of it in more of a bin fashion, you can also do ordered and unordered with that. Now the interesting one is shape. Shape in ggplot is really best for doing variables that are discrete and variables that are unordered, and that is specifically because it's hard to come up with a natural ordering of shapes that at least R has access to. You could do something silly like, add an edge for every higher variable, but that would be really very confusing and hard to see. So that's the basic idea. Any questions on these, the aesthetics and what sorts of variables you can graph? Yeah.
It sort of seems like size would be ordered, maybe.
Ordered?
Maybe.
Could be ordered.
Like something is getting larger, I don't know.
Yeah,
How
but
would it be unordered, I guess?
well, it could be unordered. You could just assign it that way. You could basically say to the program, like, well, I want you to assign a size factor to here, but you'd be assigning the size factor to discrete variables, right, that have no obvious ordering. And so, our ggplot would order it in some fashion and would pretend that it had an order, but in fact, the interpretation of it, you couldn't interpret it like, oh, this point is bigger than the other point, therefore it is more of whatever variable I've assigned to that aesthetic. Yeah. Okay. And then the last thing, which is pretty cool here, I think we've got everything into this. So, if you want to create a nice little facet plot like we did before, and you want to, say, add a smoother or some sort of statistic to each one of those panes, again, you have to think about layers in ggplot. So what you're doing essentially is adding another layer on top of that already pre-existing trellis graph, except this layer only has a series of linear regressions in it. And you can use this doing geom smooth. There's a whole side of ggplot that uses that will sort of map different statistics onto these graphs. So you could use stat smooth and you would get the same exact thing. But the basic idea here is right. Let me just make sure this works. That we would get this this graph. So this is our baseline graph, right? Now if we just want to add, say in this case, a smoother, all you have to do is fill in the method. And in this case, we're using the LM function. We want to fit an ordinary least squares regression to this. And I put in some extra aesthetics here. I made the color red, and I made the size 1, just so the line appears a little bit thicker and it's a little bit easier to view. So if we go ahead and graph that same thing once more. Let's see. You can see it does the same exact thing, and if we zoom in on it here, we can see that we've got that same exact plot, except now it's got a linear trend line on there, and you can even see, if you look in real close, it's included some confidence intervals around each one of those points. Again, that's another option that you can take off. And just note that you're not limited to doing an LM regression here, right? I'm pretty sure with this statistic, you could also feed in something like the low S, fit a low S curve, basically a local ordinary least squares regression to it. That should work. Yeah. So if you see here, where the fit is smoother, it's not limited to being linear, and you can do this for a lot of things, and it's really easy. You don't have to go back to LM and say, all right, give me regressions for each one of these factors. You know, ggplot takes care of all of that behind the scenes, and it's really simple for mapping things. So, are there any questions on this? The what? I wasn't planning on it, but there is this black and white option if you don't like color. Yeah. Yeah, I don't remember what it is off the top of my head, but if you look in the documentation, it will say, do you want the theme of this entire graph to be in black and white? And then you just add another layer. The call is something like, theme black white or theme grayscale with empty parentheses, and then it will just take out all the color in the graph. Yeah, I don't tend to keep these things in my brain because I'm on that website most of the time. So, any questions? If not, I think we're good.